All right, we should be recording now. So this is not at all the slide deck that we've looked at this one weeks ago. That's the wrong one. Apologies. This is the right one. Here we go. Okay, so today we're going to be talking about networking. Networking is complicated. Networking is difficult. Networking is very conceptual. I don't know what exposure you all have had to networking in the past. Let me make sure I'm in focus here. But I am. Cool. I'm going to try and give like a kind of high-level summary. I will also note that networking is not my expertise. I write apps, so I write clients, just client-side code. I have, on occasion in the past, done server-side things. I'm not good at it. I don't enjoy it. Networking was one of my least favorite classes when I went to college, because it is just so unnecessarily complicated. And the reason for that is just historical in nature. It has to do with how the web exploded so quickly, and it has to do with how things got built on top of each other very, very fast. And if you talk with someone who knows a lot about networking, they'll tell you that the internet is held together with bubblegum and wishes. And from everything I know, I think that's true. The main thing is just, I'm going to give this high-level overview. This is specifically from the perspective of someone writing clients. So as a person who writes apps that use services, okay, online. I'm sure there are other classes that go into the other side of things. So, okay, so to start with, before we can talk about client-server relationships, we need to talk about a word that I've used a few times now, and I've never really explained or defined, which is API. So API is a word that gets, or an acronym that gets kind of overused, but it's also almost always used correctly. It just applies in a lot of cases. So what is an API? API stands for Application Programming Interface. That's a bunch of fancy buzzwords. What is it? What is it actually, right? The API is the public-facing portion of a code base. So essentially, when you write code, if you have anything in your code that is exposed for other pieces of code to use or access, then that is your API. It is how other code interacts with your code. When other code uses your code or someone else's code, they are called clients. So while you are building an API, you are building the API for your clients, okay? When you are a client using an API, then you are the client. Client is another overloaded word. Client can mean the customer, it can mean the end user, it can mean the other developer using your code, and it can also mean like applications that run on iPhone or desktop that then interact with a service, right? It's overloaded, but generally speaking, the reason it's overloaded is the same reason why APIs are overloaded. Those are all actually correct. So an API is a contract. You can think about it as a contract between two pieces of code, two distinct programs, if you will. How can they talk to one another? How can they use one another, right? Of note, some examples here. Whenever you import Foundation on the top of your file in Swift in order to access some functionality that you couldn't access by default, that is an API. You are calling and using one of Apple's most basic APIs, and anything you use that requires that is a part of the API. So this contract includes, but is not limited to, functions, interfaces, and versions. And versions are their whole own other thing. So we'll get into those in a bit. And then APIs also typically include documentation describing how to use them. If you are writing an API, please document it. Please create documentation. They've made it so easy nowadays to make documentation. You can just put it in front of your function. And we'll see some of that later on as well. So, why do we use APIs? What's the purpose of them? APIs allow us to remove complexity from our clients. Rather than copy and pasting our code everywhere, right? Rather than me posting my code on a forum and saying, hey everyone, look at this. It makes widgets or whatever, right? And then everyone's like, oh wow, that's really cool, that's so nice. And they copy and paste it into their code, right? That's pretty inefficient, right? Let's say that I then have an update and I'm like, oh look, cool, my widgets are now blue instead of green. And everyone's like, oh, blue is so much better, right? If they want to get the update, they have to copy and paste the code from the forum, the updated code from the forum, into their code base. It's a nightmare, right? So APIs allow us to kind of take complexity out from clients and put it somewhere else. This sounds like functions, kind of, right? How functions can be used to create small pieces of code that you can then call from elsewhere. And that's because it is like functions. In fact, APIs are pretty much just functions and types, right? That you can then use. It's just, rather than having it all be in your code base, you can also use someone else's code base. So they simplify your client code. These two bullets mean the exact same thing. Apologies. And they also allow you to access resources and data over networks. Most of what I've talked about so far has to do with client-side APIs, things that you use kind of and bundle in with your code. However, you can also use APIs to access resources and data over networks, and we'll take a look at that too. So let's talk again, though, about local APIs. So these are also what you'd call dependencies. You might remember when we quickly looked over Swift Package Manager in the very beginning of class, and you've used it a little bit since, but we haven't really needed any dependencies. If you ever pull in a dependency that your code can then import and use types and functions from, that is a local API. Basically, you're doing that copy-paste thing that we talked about, except the package manager is kind of doing it for you and it's bundling it up, and the code isn't all technically there, it's already kind of compiled, and you just have all the interfaces, right? And a bunch of binary that'll execute correctly. So package management systems like SPM chain different libraries together. So a library is something that can be used as a dependency, basically. Code is downloaded and linked automatically as part of compilation. I'm describing what I've already said. And then each one builds on further dependencies by using their APIs. So what you end up having happen over time is that, basically you get these huge dependency graphs where someone writes this really important, super helpful piece of functionality that everyone wants to use, and they're all going to implement and depend on it, right? And so you have a bunch of those kind of low-level things, and then you have higher-level things built on top of it, higher-level things built on top of it, and higher-level things built on top of it. And you just get more and more stacks and a bigger and bigger dependency tree as you get into higher and higher levels of functionality and more things that you can do. If this sounds like how programming languages work, with binary code, assembly, and then an interpreter or a compiler or whatever, and then code, it is, right? It's the same kind of thing, right? There's these kind of fractal similarities exist all over programming. So the other thing to note is that when clients are using local APIs, they set the version of the dependency that they use, which changes the API. Basically, we'll talk about versioning a little bit, but when you're using a different version of the same API, its interface might be slightly different, right? So the API might be different. There might be different types or different functions, or they were changed or something between different versions, right? So it's essentially a new API. All right, so you can also end up in something called dependency hell. This is when your dependency graph becomes extremely convoluted. For example, let's consider A and B depend on C version 1. C then updates to version 2, which means that B, the B maintainer updates their code, right? So they make sure that their code works correctly with V2. A now does not. Whoever is using A, or whoever is building A, they dropped off the face of the earth, right? They maintained a GitHub repo with a dependency that was great, and you really loved it, and it was doing all the things you wanted. And then you see that the last update was like 4 years ago, right? They haven't kept it up to date, and now C for A is using C version 1 and B is using C version 2, and you're trying to use both A and B in your code, right? This can create an incompatibility, and it can actually cause a break in your code depending on how it's all being done and set up. So this example is simple. We're talking about 3 dependencies that are doing versions and updates. Production code can have hundreds and hundreds and hundreds of dependencies in their dependency graph. So you end up with this dependency hell situation very frequently. It can also eventually lead to what's called dependency lock, where you can no longer update your own API. So if you're building an API or an app or something and you want to go to a new version, you find you're in a situation where in order to get to that new version, you're trying to use a certain amount of functionality from one dependency, but another dependency is keeping you from getting to that. You'll also find this a lot with language updates and various and sundry things and developer notes. People will frequently talk about how we'd love to get onto .NET 5 because that came out 10 years ago, but we can't because this dependency we're using that's vital for what we do was abandoned in 2010. And we've been trying to update it ourselves, but the person who wrote it in Haskell. So we have no idea what we're doing, or something like that, right? So one of the solutions that have come along to kind of help with this is something called semantic versioning. It helps, it does not solve it. Semantic versioning is basically this format. You've seen it before, you've seen it around if you pay any attention to like the little version numbers and anything on stuff. Everyone uses semantic versioning now. Not everyone, I have to always caveat that, but primarily now, most folks use semantic versioning. Semantic versioning breaks your version down into a major version, a minor version, and a patch version. So when you are doing a release, when you are releasing new code, either you're updating your API and posting a new release on GitHub that people can then pull down and use a dependency, or you're publishing your new app to the App Store, a new version of your app to the App Store. Semantic versioning dictates that you can only increase your number with every release. So even if you were to say roll back your code and because you released a big bug to production that brought down the entire website and you need to roll back, you might do the rollback in code, undo, Control Z, Control Z, Control Z, right? But when you kind of do your release, you update your semantic version to be one higher than it was before, okay? Now, of note, something that always used to catch me up with semantic versioning, whenever I would see 1.10, I would think, oh, like 1.1, got it, right? Like 1.1, because if you truncate everything else off that like you do normally with a single decimal, then it's just 1.1, right? The main thing to note is that 1.9.2 is a lower version than 1.10.0, okay? Basically, instead of saying 1.10, you say 1.10, 1.11, 1.12, that sort of thing. And those can increase, ad nauseum, right? So basically, your rightmost one needs to have gone up, or your middlemost one needs to have gone up, or your leftmost one needs to have gone up, right? And if your middlemost one goes up, then your rightmost one resets. If your leftmost one goes up, then your middle and right both reset as well to 0. When you have a major version, they signify an API has been changed in incompatible ways. So essentially, when you update an API to a major version, when an API is updated to a major version, they are saying, hey, this release changes things that may break your application if you use us. If you are depending on us and you pull in this latest version, you're probably going to have compiler errors because you're calling functions or types that don't exist anymore. So that's what major versions are for. They're a big deal. They're intended to signal to users of your API, hey, check it. You're going to have some stuff that you have to do. You're going to have to update, okay? Minor versions signify API changes that add new functionality, but they do it in a backwards compatible way, which means that your code should be able to update the minor version like pretty consistently without having to make any changes to your code while still receiving improvements in the existing API that you're using. Then patch versions, the final kind, signify API changes that are backwards compatible, much like minor versions. However, they perform bug fixes specifically, as opposed to adding new functionality. So they just fix existing bugs. Now, here's one of those weird things where you're not supposed to have to change your code for patches, right? But if your code relied on a bug, if you expected a bug to be the way it was, and then you built around that, you're probably going to want to change your code because it won't work anymore. Yeah. Okay. Any questions about semantic versioning before I move on? I know this one's a little fiddly. Cool. Okay, so let's talk about a modern contract. So nowadays, an API contract tends to look like this. The first statement of the contract is that a client will not be required to edit their code to keep using the API for patch and minor version updates, as I said before. Another line to the contract, if you will, is that a client may be required to edit their code to keep using the API for major version updates. So major version does not necessarily have to change the API in a breaking way, but it's allowed to. They have the right. That is their choice. An API provides explicit and clear documentation regarding how it is used. This is more of a wish list item from me. I wish this was true. It should be true. It is not often, but it is what it is. An API exposes only what is needed to accomplish the tasks it was built to do. So this one's really important. This one is basically the idea that if you're writing a library, and your library writes books for folks, right? You have all sorts of internal classes and functions that are creating authors and worlds and settings and characters and everything, pulling them all together, right? But the whole point of your API, the purpose of it for your clients, is to give a book. Your API might have a single function, get book. And that's the only thing that's public facing. Only thing that in your code is marked with the public keyword. Everything else is all internal or private. And anyone using your library doesn't have access to it because they don't need to know about that. It's not important to them. And then when we're talking about networking specifically, and this will make more sense once we talk about networking a bit more, services will respond to requests matching at least one previous major version of the API. Basically what this is saying is, if a service updates to a new major version, they at least promise that they're not going to immediately break all apps that are currently using the existing version of the API. That there's a grace period in which they can update their apps to use the new API. So, when you're looking at Apple's docs online, you'll see stuff like this. This is the documentation for tasks. Task groups, actually, specifically. That's the add task function right there that we talked about for the quiz, right? So this gives a bunch of information. It tells you the types of all the different properties, or parameters, sorry. It tells you the return type. You can see the function definition, and you even get a little bit of text that tells you what you should expect this to do, right? Add a child task to the group and enqueue it on the specified executor, right? Executor is an implementation detail of actors. You don't have to worry about it too much. So this is an API. This is sort of what API documentation looks like, right? You can also look at it when you click on Add Task, you can get more details, right? And a well-documented API has a lot of details. It has a lot of information for you, right? Here we can see, oh, cool, here's like the function definition in Swift. Here's like this available when child task result conforms to sendable. Here's descriptions of the parameters. Here's all the versions that it works on and exists on, right? All that stuff, okay? So this is kind of what like APIs look like when documented well. It tells you everything you need to know about how you can use this code for yourself. You can also look at APIs in Xcode. This is, wow, that was reversed. Okay. Sorry about that. Animations were messed up. I never debug. Don't be me. So if you hold down Command and then click on any function that's being called, any type that is written out, you will get taken to something that looks like a Swift file, but isn't exactly a Swift file, right? It's basically kind of only the definitions of a particular API for Swift, and it's all slammed into one file. So as you can see, this is 5,000, like line 5,258 out of like 20 in this particular one, right? So it's quite huge, right? So, but you also get, basically, you get to see the function, definition. You don't get to see the code block for it. You don't get to see how it executes because you don't care about that. You're consuming it. You're using it. You don't need to know that. You just need to know the contract. What do you put in? What do you get out? And what do you expect to happen when you do that, right? And you can accomplish that with the parameters, what you put in, with the result, with the return type, right, what you get out. And then the documentation tells you what you should expect to happen in addition to, all of that. Cool. All right, any question about local APIs? Okay. So now let's talk about server-side APIs. That was all local stuff, right? We're talking about networking, though. So what is a server? Server is a computer that is somewhere else. You can also call it a remote computer or a remote server. The idea is basically it's just not you. It's not the same box that you're running on, right? Technically, a server can be another program running on the same box, right? The point is it's somewhere else, right? It's not your code. It's some other code that's running and executing somewhere else. Typically, you access servers over the network via a domain name. Server computers are built differently than other computers. They use different motherboards, they use different amounts of RAM, different kinds of CPUs. They can have hundreds of thousands of connections to various and sundry different clients who are accessing them all at once, right? They're highly parallel. We've talked about, I made fun kind of how modern, cores for our, laptops and whatnot. They're like, oh yeah, you've got 8 cores and 12, virtual cores or whatever, right? So you get 20 whole cores, right? Server CPUs laugh at the face of that. Server CPUs have hundreds of cores, right? Which allows them to do many, many things very, very concurrently, right? And actually do it concurrently rather than kind of faking it like we tend to do with our local machines. When you have a bunch of these powerful computers together, you get a server farm. You've seen these in movies. They're those rooms with like the giant stack with all the different things and then with the lights. That thing back there looks like a server farm. I don't know if it is, but it looks like one, right? They kind of look like that. You'll have a whole room full of them. They're all together with a line, they've got little wires, right? That's like IT stuff, right? Information technology, people managing that and running those things. Those are IT folks, like admins, IT admins. They will crawl through broken glass to get the server farm back online if needed. They are people who you should have the utmost respect for and never want to be because their job is awful. Yeah, so that's server farms. The cloud, quote unquote, that everyone always talks about, are different sets of distributed server farms that share data and resources in a very complicated fashion. So basically, if you have a server all by its lonesome, then it can handle hundreds of connections. If you take a bunch of servers and put them in a room, you have a server farm, and they're all running the same program simultaneously, so they can handle thousands of connections. If you take multiple different server farms all across the United States and network them together, you create a cloud, okay? And then the cloud does all sorts of stuff like check your region and connect you to the closest server farm that has capacity for you. And it does something called sharding. And it just, there's like a million things that clouds do. And there's like, you could take like 3 or 4 classes on just distributed computing and cloud computing. And we're just not going to talk about it because to you as a client, you don't care. You're just calling it, right? You're accessing it. So, and the other thing to note is that servers are always running at least one or more services that clients can access via URL. So a service is basically that program that's running, that's waiting for you to talk to it. It's waiting for you to send a message and say, hey, please help me do something, right? So that's what a service is. Oh, no, sorry. There's a slide about what a service is. So a service is an always executing code application. It is typically accessed via URL. Wow, I covered this all very quickly. It can receive inputs, interpret them, execute code, and then return a result, right? So basically when you access it via URL, you give it a bunch of information, and then it takes that information, it interprets it, it figures out what to do with it, and then it executes some sort of functionality, and then it returns a result back to you via, the transfer protocol that's being used. If the inputs that are received define the service API. So what basically, the API of a service that is running on a server is defined as the functionality that you can access by URL with inputs. So whatever inputs you can send and get results back, that is the service API. A service is often called service, server, server-side, backend, Lambda, microservice, API, service API, backend API, right? Like these are all terms for basically the same thing as far as you are concerned. A server-side developer would look at that statement and start frothing at the mouth and get really upset with me because Lambdas and microservices are very different from regular services. But for you as a client developer, you don't care. You're just calling it. So let's talk about URLs, okay? You've seen these before. They're what you type into your web browser, right? URL stands for Uniform Resource Locator. You don't really need to know that, but I thought it's fun to know what the acronym stands for. A URL consists of 1, the protocol of the URL, the protocol that you're using to access it. 2, the domain name, the place that you're trying to go. And then 3, a path on that domain name, the place that you're trying to go within that domain. And you might also include parameters with that domain name. You can also use URLs, this is kind of a description for how to use them on the web, but you can also use URLs to find a file locally, right? If you ever see, if you open a file up in your browser like a PDF that you've downloaded, you'll see like the URL up in the top is like file : / right? And then like basically the path to it in your folder structure, that's also a URL, right? It's just a location basically on a computer. So you can use URLs on networks to access services that are running on servers. And just a little implementation note, domain names are masks for IP addresses. So basically, that's managed by your ISP, the Internet Service Provider, and a domain name service, the DNS provider. Essentially, when you go to Amazon.com, some server somewhere knows that Amazon.com is hosted on this particular IP address. And so whenever you go to Amazon.com, Amazon.com gets sent out by your internet service provider to a domain name service provider who then looks it up and says, oh cool, this is the IP address they want. And then sends that back to your ISP who sends it back to your browser. And then you can use that IP address to actually call that particular server on the internet, right? So, oh, I went back, whoops. But again, not super important for you, good to know, helpful, kind of, when you're doing like local testing, 127.0.0.1 always reroutes back to your own computer, for example. That's kind of helpful if you're ever building a server. You will not be building servers, so you don't really care. I mean, you might be in other classes, but you won't be here. So endpoints, let's talk about what an endpoint is. An endpoint is a URL to a location on a server that does something. So we talked about you use URLs to access services on servers, etc. And that is called an endpoint. Any particular piece of functionality that you're accessing on a server or on a service running on a server is an endpoint. So endpoints can be direct links to actual files for you to download. So just like the file : / path to a file, hosted on the server, they also have a folder structure. And they can link a URL, that comes in to their domain name to their folder structure and say, hey, if this URL comes in, serve this file, right? A specific code file to execute. So PHP and JavaScript are two kind of things that do this. Basically, again, it's a path to a particular file, but this time it executes the code in that file immediately, rather than like downloading it, right? You can also have an endpoint be a function call to a service, essentially. And when you have it be a function call, the service that is handling that quote-unquote route that the URL defines determines what to do. I think I talk about it later, but just of note, a direct link to actual files is how websites work. Websites have an index.html file at their root, and at any particular path that you go to, they have an index.html file, and that file is what gets rendered by the browser. That's just something all browsers have agreed upon. They say if we go to a particular route and we get served an index.html, we will render it, right? So that's how websites work. Websites, done, good job. Okay, so let's take a look at the URL endpoint format, right? This is an example. This URL does not exist. Don't try to go to it. Okay, so first we have the transfer protocol. This is basically a way of saying this is how we're going to be sending and receiving information from this particular resource or this particular service, right? It's almost always HTTPS. There's also like SFTP and HTTP if you're, back in the 2010s, before the 2010s, right, which was not as secure. Just file : // right, there's a bunch of different things you can do there, right? But primarily for us as clients using services on the web, we're going to use HTTPS, okay? Then you have after that your domain name, right? So this is your example.api.com, amazon.com, whatever, right? Whatever your website name is, right? Mine is pastadiablo.com, which has been my online alias since I was 13. If you see someone named Pasta Diablo on the internet, it's me. So you're welcome. Best of luck. This is the route. So I've mentioned the word route a few times here, and I'm going to continue mentioning it, but I'm not going to really explain it. Basically, a route is just like the path, right? It's the URL's path for that particular service. Routing is a whole other can of worms, and it's something that you do for like web apps, like React Native and stuff. And some people think that routing is the best way to do navigation, including on native apps, even though Apple has a bunch of extremely robust libraries that are not routing based for accessing different parts of your, app, but people like to use routing for whatever reason. And then lastly, we have our parameters. So you can pass in parameters after a question mark, and you pass in you say the name of the parameter, and then you say equals, and then you say the value that you want to pass in. And this is one way to pass parameters. The other way is in the body, but that's all HTTP stuff. This is just kind of basic URL definition stuff. So now, if this looks familiar to you, that's because it is. It looks a lot like function calls. Functions have an instance name that you are calling, much like a domain name. They have a function name that you call, much like an endpoint route, and they have function parameters that you call, much like or that you pass, much like endpoint parameters. This similarity is that kind of fractal spinout that I was talking about that exists, okay? Basically, this is a very common pattern up top that you see here. That's a very common way to access data from a website, from a service, okay? So basically it translates to a function call, which is what you're doing. You're calling a function running on the service. So let's talk about RESTful APIs. What is REST? REST is a set of rules for designing service APIs. It stands for Representational State Transfer. It was written as a dissertation thesis by some guy, I can't remember his name, in like 2001, right? Basically, it was this idea that like you could, for any given, domain name, you just call it with, with just do a GET request to it, and it would return a list of all the endpoints you can use. And then each endpoint would have sub endpoints within it, right? So you'd hit one and you'd hit the like main, domain with nothing added, right? And then from there you could navigate further and further down to more and more stuff, right? At the end of the day, that's not really how it's used. Using it that way kind of involves all sorts of basically that's intended to be a way for you to write generic code that can always use any RESTful API, right? Which isn't actually super helpful at the end of the day, because eventually you're going to need to translate from that kind of super generic code back to something very specific for what you're doing. So most of the time when people talk about RESTful APIs, they mostly just mean HTTP services, okay? So services that use the HTTP protocol. HTTP, if you're curious, stands for Hypertext Transfer Protocol, because everything in the 90s was hyper. That's just what they thought sounded cool. I don't know. So some key principles that are still in use by RESTful HTTP services. So some of the key components of what was originally proposed as RESTful and has now kind of become the few things from it that are actually done in industry is that URLs return HTTP formatted data that represent resources. Some URLs can be used to request state changes to those resources in the service, and the relationship is stateless. Calling the same URL with the same data will always yield the same result. Now, when I say that, it's one of those, technically, because you can make a request to change resources on the server, right? If I have a resource that's like a piece of text, right? Like a title, right? My title, right? And then I use a URL to request I change the name of that title to your title, right? Okay, well then the next time I call, the get that title, it's gonna say your title instead of my title, right? But the point is, it's still returning the same resource, right? It's just the resource has been changed. So this statelessness, the fact that like calling the same thing yields the same result, is one of the kind of most important ideas of REST. It's also the one that is most often violated by JavaScript specifically, or PHP, if you will, if you're older, right? Basically, if you ever go to a website and you want to hit back on the back button, but you're inside of a little form, right? And the form doesn't let you go back because your URL hasn't actually changed whenever you move forward in the form, that's JavaScript breaking stateless relationships, right? That's basically a non-RESTful API messing you up and requiring you to use their shitty little back button that they put in the lower left corner where no one would ever look for it, right? If this experience I have is not universal, I apologize. So, why are we using REST on HTTP? Most often, services define an input and an output for a database. So typically, when you are dealing with a service online, when you are calling a server in a service, they are essentially a wrapper over top of a database, some persistent storage that is accessible to everyone using the service, all the applications that use that service. That is basically like Reddit, if you will, right? Every Reddit user can all see all the posts on Reddit, right? And those posts are stored in a database, right? And everyone can see it, everyone can add comments, right? And those comments get put in the database, right? Reddit, the website, is basically just a fancy kind of looking wrapper that kind of displays the data stored in the database in a way that is nice to read for us as people, right? That's most web applications are that. Most web apps are a pretty way to look at data stored in a database and to change and easy ways to change that data. That's kind of it. It's most of what we do. That's most of what we do here, right? Old joke. So REST as a pattern allows safe access to the data on the server because it's stateless and doesn't require like a session and mutability and whatnot. Then it is safe access for data on the server. And some guy was just staring at me. It was interesting. So it is easy for clients as well. As a client using a REST API, you only ever expect to hear from the API, to hear a response back after you send a request. So you send one request, you get one response. It's a one-to-one back and forth stateless relationship, right? It's a transaction, right? Much like when we use await to make a modification or sorry, not make, but to enqueue kind of accessing something, right, in async await. If we use await to call a function, right, we are basically we call the function, so we send the request, and then we wait to get a response, right? And there's only one request and one response, right? Same thing here. So responses with HTML in the body can be rendered by browsers. This is the thing I was talking about before. So if the response comes back with HTML in the body, or if it's just an HTML file, or whatever, anything that's HTML can be rendered by your browser, and that's literally how websites work. It's not actually literally how they work, but it's good enough for you, because you're not building websites, not in this class. So how do we use REST on HTTP? Well, here's another acronym for you, because I've already given you so many. I figured you need another one. This one's called CRUD. CRUD. It is for basic actions of persistent storage. So when you have persistent storage, like a database, or just files, a file system, right, on your own computer, there's only 4 things you ever really want to do with those files. You want to CRUD them. You want to be able to create them. You want to be able to read them. You want to be able to update or edit them, and you want to be able to delete them. That's it. Everything that you could do to a file falls into these 4 categories, conceptually. So, CRUD. Software engineers have a weird sense of humor. So, when you're using REST on HTTP, you can send a request to the server, you get back a response, as we were saying before, just like with sending an await request and getting back a return response in async await. Both the request that you send and the response that you get back, the format of an HTTP request and response have something called a head and a body. This is helpful if you're ever looking at them directly, and it's also relevant for some of the requests that we're going to send. Some particular kinds of requests require you to make modifications to the head and the body, right? REST on HTTP CRUD. So when you want to use CRUD operations for a REST on HTTP service, you will typically use there are some specific resource methods that HTTP defines. Put, get, patch, and delete. These directly translate to CRUD. Put creates, get reads, patch updates, and delete deletes. That's the only one that they matched because, fuck us, right? The interesting thing about these direct resource methods is that they're used specifically for editing files directly. The thing is that most of the time when you're accessing services online, you're not accessing files directly, most of the time. And even if you are, like with index.html, you only have read permissions. So as a result, get gets used all the time. Get is constantly used. It gets overused, right? The get method, right? Put, patch, and delete don't really get used much. Really, not really. They typically don't get used. because there's a different method that gets used instead, which is called POST. So POST is basically a way of saying, hey, I want to send some data to the API at a specific endpoint, and then the API can decide what it wants to do with it, right? I don't care what the API does with it. The API can do whatever it wants with it, right? Put get or put patch and delete all kind of have an implied statement of, hey, API, you're creating with this call. You're creating, right? And patch is like, oh, you're updating this file. And delete's like, oh, you're removing this file, right? Post doesn't care about that as a part of the method, right? The method is generic. It's just saying, hey, API, here's a message, and here's the data, right? The thing is that the reason why post gets used very frequently, and sometimes get does, which is really interesting, is because the endpoint itself will typically imply the operation being performed, right? So if you're ever on a website where you're building like, a new blog post, you'll probably note in the URL somewhere in the route, after your domain name in the route, you'll see like, slash, create new blog post or whatever, right? And then slash some random string of numbers, which is the ID that they've assigned to your new blog post editing thing, right? And like so on and so forth, right? That is why those three don't get used very much. It's mostly because you can just use post and the API route already tells you what you're going to be doing. So you don't need to use those resource methods. There's a lot of things like this in web development that is vestigial, things that exist because someone thought they might be helpful one day and then they ended up never being helpful. Yet, those things still do get used on occasion, right? Maybe not in a public-facing way, but if you're building like an enterprise application, or if your application has access to a service that only your app can access, a private service, right? Like for example, Amazon. Amazon's app can access services that no one else in the world has access to, right? In that way, put patch and delete might actually be useful, right? But generally speaking, you don't want the general public who have a web browser to be able to put patch and delete files on your system. So you tend not to make those methods available. You don't respond to them. You give back an error of not implemented, right? So yeah, as I said, most clients only ever use get, even for editing data, which is wild. So streaming APIs are a different kind of API. I'll talk about them very briefly. These are event-driven rather than RESTful. Basically, you kind of say start, right? You open the stream, and then you kind of just receive events over and over and over again on it, right? This is technically, it can be done with like WebSockets or TCP. That's not really relevant. The main thing to know is just that streaming APIs, you say, hey, I want to start receiving stuff, and then you basically receive stuff over time as it happens. Some examples of things like this are very large pieces of data such as videos, right? You'll notice on YouTube when you're watching, there's that little like section of lighter gray rather than the darker gray just beyond what you're watching. That's called the buffer, right? That is what you have so far streamed down, right? And then your browser remains open in a state to receive new chunks of video data as you get closer, further and further along in the video, right? Live updating data such as Wikipedia recent changes feed, or more generally speaking, like RSS feeds, right? These are just, feeds that are kind of constantly putting data out there, and you can, if you want, just kind of open up a socket and say, hey, I would like to receive all the data as it comes in live. Please, I will keep this open, and I will take any data you give me, right? So rather than having that one request and one response, you kind of stay in this open state and just keep getting events from the service, right? Also, live updating large data like video streaming, aka Twitch. Video streaming is live updating data, but it's also large, so it's distinct from the other two, but not really. Okay, that was the client-server relationship stuff. We'll talk about client-side networking and actual Swift stuff in the next segment. For now, you've got 10 minutes. Feel free to ask me any questions as well, if you've got them. So.
要去吃吗？可以一点点。